Hello everyone, myself Michael Ravina, Associate Professor, Department of Computer Science and Engineering. The subject is CS3551, Distributed Computing. The unit is Logical Time and Global State. The topics are causal order and total order. Causal order can be described by using the Raynal-Schiper-Toueg algorithm. In this algorithm, there are two important steps. First one is the send event, then second one is the message arrival. In the first part, that is means first one is the local variables are declared, then after that array of int, that means sent and delivery of messages are described. Then first send event, when PI wants to send message M to the particular PJ, that means process PI want to send the message to the process PJ. Then first step is the send of M comma send to PJ. If the send of I comma J occurs before the send of I comma J plus 1, then next one is the message arrival step. Message arrival, when M comma ST, that message arrives from PI from PJ, then deliver of particular M to PI when for each process X. Deliver of X greater than or equal to ST of X comma I, then particular sent of X comma I is before the max of sent of X comma I comma ST comma X. Then delivery of particular message I2. How does the algorithm simplify if all the messages are broadcast? The correctness was described by FAFO channels and safety. Then it contains some liveness, that means assuming no failures, finite propagation time. The complexity of algorithm is n square in or processes, that means time per send and receive event is n square. Optimal KS algorithm for causal order. It contains the following principles. The optimal KS algorithm contains the first one is the delivery condition, that means delivery condition for correctness. The message M that carries information D belongs to M, then where the message M was sent to D in the causal part of the sent M star and it not delivered to D. Necessary and sufficient condition for optimality. Here, for how long the particular information D belongs to the M is stored in the log at a process and piggybacked on the messages. As long as and only long as propagation constraint, then propagation constraint 2. Propagation constraint 1 means it is not known the message Mi delivered to D. Propagation constraint 2 means it is not known that the message has sent to the particular D in the causal future of sent of Mi comma A. Hence, it is not guaranteed using the reasoning based on the transitivity. If either the propagation constraint 1 or 2 is false, D belongs to Mi must not be stored or propagated. Then this is the algorithm. Here same, first one is the local variables are declared, then after that sent, that means sends a message M to this, that is first the clock J is defined, then after that for all D checks a particular clock of messages, then after that for all O belongs to the particular OM, then modify the receiver. After that if D J belongs to the particular O, then D that receiver sends to the sender sends the message to the particular receiver. Like this, these steps are processed in the optimal KS algorithm. This is the continuation, that is here this is the receive part. First one is the send part, then here this is the receive part. In the receive part, first the delivery condition. After the receiving the message, the particular message is who sent the particular message is recognized after the particular delete. Suppose the now the redundant dependency of the message is represented by the particular receiver or sender, then that has been deleted or never inserted. Then delete all the marked elements in the OM and log. After here the logs are maintained. Then after the final, purge all the null index. The next one is the total message ordering. The total ordering here, for each pair of processes PI and PJ, for each pair of messages MX and MY that are delivered to both the processes. PA is delivered message MX before MY if and only if PJ delivers the MX before the MY. This is the total ordering. Here the centralized algorithm is used for total ordering. Each process sends the message it wants to broadcast to a centralized process, which relays all the message it receives to every other process over FIFO channels. When process P wants to multicast a message M to a group, then send MI of I, G to a central coordinator. This is one of the central coordinator. When MI of, this is the code, that means when M of I, G arrives from PI at the central coordinator, then send off M, I, G to all the members of the group. When M of I, G arrives at the PJ from the central coordinator, deliver M of I, G to the particular application. The complexity of each message transmission takes 2 message hops and exactly n messages in a system of n processes. The main drawback of the centralized algorithm is single point of failure and congestion, and it is not an elegant solution. So this is a major drawback. Then so far 3-phase distributed algorithm is used. This is a 3-phase distributed algorithm. In here the first phase, that means in the center side, the 3 phases can be seen in both sender and receiver side. In the sender side, the first phase one is in the first phase a process multicast a message M with a locally unique tag and local timestamp to the group members. In the phase 2, the center process awaits a reply from all the group members who respond with a tentative proposal for a revised timestamp for a message M. Then the await of call is non-blocking. In the phase 3, the process multicast the final timestamp to the group. This is a format for center side with the 3-phase distributed algorithm. Here the 3 phases. First phase is when process P wants a multicast message to the with the tag. Then second part is when revise the particular. Then third part is the multicast timestamp. These are described in this code. Then next one is the total order distributed algorithm. That means the distributed algorithm example with complexity. This is the example for the particular algorithm. The complexity of 3 phases are 3 of n-1 messages of n-1 test. So delay of 3 messages also implements causal order.